So we can calculate the amount of heat in kilojoules needed to convert 1 mole of ice at 25 degrees C, negative 25. Oh, right, this is the thing that we just did. But which of these graphs describes that process for each of the steps? Try and keep everything relevant on the screen. So we're starting at negative 25 degrees C. And then we're heating to 37 degrees C. So this is water, right? So it has to melt at some point. It's A. So for A, we start here at negative 25, go up to 0, and then at 0 is where the water starts, or the ice starts melting. So then that temperature stays the same all the way across. And then at some point, we'll have melted all of the ice. And that's when the temperature can start increasing again. So B doesn't include that heat that it requires to melt the ice, to break those sticky bonds. And then C includes the difference in specific heat capacity. So it takes less energy to heat up ice than it does water. So that's why the slopes of those lines are different. B is missing, well, it's missing all of it. It's only using the specific heat capacity of water. It's not including freezing. Yeah. So sublimation is a physical change from the solid state directly to the gaseous state. And when a substance sublimes, the molecules leave the surface of the solid where they are held less tightly than in the interior and become gaseous. And this happens with ice in your freezer even. So dry ice, solid carbon dioxide, does not melt at atmospheric pressure. It just goes straight from the solid to the gas, which makes it great in drinks at parties because it makes a bunch of, what is it? I guess it's just CO2 gas, but like white mist coming out of your drinks. So Halloween's passed, but we did that at Halloween. Just make sure you don't put the CO2 in your mouth. Dry ice, unlike regular ice, doesn't float. It's more dense than water, so it sinks to the bottom of the drink. So you don't have to worry about that too much. If the dry ice touches your mouth, there's a very good chance that it will cause like frostbite. But yeah, it does stay at the bottom of the drink. I've done this a few times. But you do have to don't give it to kids. Moral of the story, don't give it to kids. Because you don't want to hold it in your hands either, because it is negative 78 degrees C. So yeah, dry ice, solid carbon dioxide, doesn't melt, just turns into a gas. And partly because of this, you can't keep it for very long either. So if you want to have dry ice for a party, you have to go and buy it like that same evening, afternoon, like right before you're going to have people over. And it'll be gone after, well, it'll be gone before the night is over if you leave it on the counter. If you put it in the refrigerator, you'll have a teeny bit left after maybe a day. So it sublimes pretty quickly. Regular ice also does this. This is what causes freezer burn. And it's the reason that you need to have a defrost cycle on your freezer, because the ice in the freezer will sublime slowly, and then it will condense back into a solid ice on the coldest elements at the back of the freezer. And it'll slowly build up layers and layers of ice if you don't defrost it. For food, that's the next one. For food, the water will sublime out of the food, and that's what makes it, well, that's what causes freezer burn. Hard, dry, and gross if you leave something in the freezer for too long. If you get a deep freezer, I don't know what the temperature of a deep freezer would be, but you can reduce that sublimation. So it'll just take longer. Oh, right, now we're going to sort of switch gears here and talk more about intermolecular forces, the stickiness of molecules, and what causes it, that kind of thing. So intermolecular forces are electrostatic forces of attraction between molecules. So unlike the Lewis structures that we've been drawing, where we have formal bonds, shared electrons, these are just sort of, well, it's kind of like polarity, where we talked about those dipole moments, where you get positive charge on one side of a molecule, negative charge on the other side, and those differences in charges cause them to stick together. So strength of the intermolecular force determines the state, solid, liquid, or gas at room temperature. And again, if we have strong intermolecular forces, you get liquid, solids. Weak intermolecular forces tend to result in gases. So a big part of this section is going to be, well, for you to be able to do on an exam, is to rank the strength of intermolecular forces. So I think we're going to start with the weakest force and then progressively work our way up to the strongest intermolecular force, which will be present in the stickiest molecules. So the dispersion force is the weakest, and it is present in all molecules and atoms. They're also called London forces because the guy who discovered them, or at least hypothesized about them. The dispersion forces are caused by fluctuations in the electron distribution within atoms, molecules or atoms. These are all very small fluctuations, but essentially you're used to saying either in your textbook, digital, or on your physical version, right? We see molecules as these static, like sticks and balls combined together, and they don't move. And that's a fine model, but in reality, they are in constant motion, in very chaotic motion. And the electrons are in motion around them as well. So as the atoms, molecules, and their bonds move around, those electrons are also moving around to follow those. And because of all of this movement, sometimes the electrons get shifted to one side of the molecule more than the other side. And then they quickly spring back. But that's what it says here. At any one instant, may be unevenly distributed. And it's that uneven distribution of those electrons that causes dispersion forces. So they're called instantaneous dipoles when you get these uneven distributions. So the electrons sometimes will be on one side of the molecule, then they shift to the other side of the molecule, then they're evenly distributed, then they're on the top of the molecule. They're constantly in motion. So in our 3 frames here, these are roughly on either side of the helium. Yeah, you can see those. These are on other sides of the helium, so there's no unevenness in that charge distribution. But in frame 3, both of the electrons have ended up on one side for an instant. And in that instant, we're going to be using these symbols again. So this one means slightly negative. And this one is slightly positive. So then we get one side with those electrons becomes negative, the other one becomes positive. And that's just for an instant. So if you have one molecule that forms an instantaneous dipole, and it's next to another molecule, it can induce an instantaneous dipole in the neighboring atom. So because this one has randomly shifted all of its electrons to one side, that made the other side of that molecule positively charged, which attracts the electrons from the neighbor next to it, which induces another instantaneous dipole, and that pulls on the electrons of the neighbor next to it. And so for everything, there's this constant bumping and jostling of the electrons, shifting from one side to the other, causing these instantaneous dipoles. And it's a very, very, very weak force. So the dispersion force occurs as these neighboring electrons bump into each other. Positive end attracts the negative end of another molecule next to it. Partly they are weak because they are transient, so they're constantly appearing and disappearing. So even though there's a little bit of a force there, it's only there for a fraction of a second. So the magnitude of the dispersion force depends on how easily the electrons in the molecule or atom can polarize in response to an instantaneous dipole. So if it's easier for the electrons to shift to one side of the atom, then you'll get stronger forces. You'll get stickier molecules because of this. And one of the things that can make that easier is a larger electron cloud. So it's kind of like having a, anything I demonstrate with? No. It's kind of like the difference between having a, I guess we'll say a bowl of water, right? And you can slosh that little bit of water in the bowl back and forth, but it doesn't go to one side for very long, and it comes back. But if you had like a kiddie pool full of water, when you slosh that, there's more room for the water to move, and more water that's moving with it. And so it will slosh to one side and then slosh back, but it'll do it, well, it'll spend more time sloshed to one side than it would in your small bowl. So the larger the electron cloud, the more slosh room there is for the electrons. And in terms of determining strength of dispersion forces for any given molecule, one good indicator is molar mass. It's not the only thing, but for similar molecules or atoms, it does work. So if we look at the noble gases specifically, helium through xenon, we can use the boiling point as a proxy for how strong their dispersion forces are. So all the noble gases, right, they have octets. They don't need any more electrons. They're not forming bonds very readily. They're pretty satisfied hanging out by themselves. So they don't have any intermolecular forces aside from the dispersion forces, aside from bumping into each other and creating instantaneous dipoles. And then the boiling point, as we talked about, is related to those intermolecular forces, because if the molecules are stickier, then it takes more energy for them to turn from a liquid to a gas. So as we increase the molar mass or the size of these molecules, the boiling point goes up. Of course, these are all still very, very cold. 4.2 Kelvin is just like 1.5 degrees warmer than space. 1.5 Kelvin warmer than space, which is about 2.7. So the other thing that's happening here that's not really explained by the molar mass is that for every row down the periodic table that we move, we're adding another shell of electrons. So you're adding more and more shells, you're adding a larger, well, you're going from the bowl up to a kiddie pool of electrons. And so when those electrons slosh, they're able to slosh more to one side or the other. And the molar mass is also kind of a proxy for that. So not just directly describing it, but tells you something about it. So if we're to look at two hydrocarbons, I'll just draw out these structures. So you have the first one, CH4, and C2H6, which you just did on the Lewis structure worksheet. So which of these would have a higher boiling point? Yeah, has a higher molar mass. These are similar molecules, right? They're both made of carbons and hydrogens. And so we can use molar mass to say, oh yeah, higher molar mass also means that it's got more room for those electrons to move around. So this would have the higher boiling point. And without any other intermolecular forces present, that's all we need. It is. It is. It would be a tetrahedral.
Oh, because there was a question on the...
Like this part?
Yeah, just that part.
Yeah, so this is still a bond to another atom, so we would still count that for our electron groups. But we would kind of ignore you're kind of ignoring the fact that there's these other hydrogens out there. We just say, it's kind of like saying, oh, let's replace that whole CH3, this whole other part, with a hydrogen. What's the molecular geometry of that?
It's because on the worksheet there was like a question, like, what shape is it only focused on one side of the C?
Yeah. So that's what it means is include that bond, but ignore the rest of these other things that are attached on the other side of that bond. Here. So dispersion forces are the weakest. Essentially boils down to, excuse the boiling point is affected, sorry. It essentially comes down to how much room there is for electrons to slosh around. And if you're comparing similar things, like all of the noble gases or different hydrocarbons, you can just use molar mass to figure out which one's going to have stronger dispersion forces. So moving up from dispersion forces, go up to the next strongest is Dipole-Dipole Force. So the Dipole-Dipole Force exists in all polar molecules. Does not exist in nonpolar molecules. This is where you got to go back to end of chapter 10, where we used Lewis structures to figure out if something's polar or not. It really comes down to if it has lone pairs, it's polar. If it has, if one atom is more electronegative than the other atoms attached, then it's also going to be polar. So these are permanent dipoles. So in all of our other stuff, right, those dipoles are instantaneous. They only happen randomly or when they bump into another atom or molecule. Polar molecules have permanent dipoles. So one side of the molecule is always positively charged. The other side is always slightly negatively charged. And so it's the attraction between the positive end of the one permanent dipole and the negative end of another, kind of like magnets. So all molecules have dispersion forces, but polar molecules have dipole-dipole forces on top of that. So because of this, because they have permanent dipoles, they have stronger intermolecular forces, which means that they have higher melting points and higher boiling points. So it takes more energy to melt them, more energy to boil them. So a molecule like formaldehyde is a polar molecule, has a permanent dipole because you've got the oxygen on one side and you got the hydrogens on the other side. So then if you get two of them, the positive end of one and the negative end of the other will be attracted to each other and they'll sort of snap together. So that's the dipole-dipole force. And again, we can use melting point or boiling point to sort of, in a roundabout way, look at the intermolecular forces. So formaldehyde has a molar mass of 30, its boiling point is negative 19.5 degrees C, negative 92 degrees C for the melting point. But if we look at ethane, has almost exactly the same molar mass, but it is a nonpolar molecule. And so its boiling point is negative 88 degrees C, and its melting point is negative 172 degrees C. So much, much weaker intermolecular forces, so it melts and boils at much lower temperatures. So exam questions, another good exam question, for example, would be, I give you the boiling points or melting points of a few different compounds, and I say rank them according to their intermolecular strength. So if something has a higher boiling point or a higher melting point, that means it has stronger intermolecular forces. So polarity of molecules also affects miscibility, which is the ability of two liquids to mix. And we did talk about this at the end of chapter 10. So polar liquids are miscible with other polar liquids, but are immiscible, so they don't mix, with nonpolar liquids. This is often described as like dissolves like. And this really comes down to the polar molecules just stick together so much more strongly that they squeeze all of the nonpolar molecules out because they don't stick to the nonpolar molecules. That's why if you don't have soap, you can't really wash off oil, even cooking oil, off your hands. So pentane does not mix with water. And so this is like a diagram of pentane. I think this is the same one we had in chapter 10. We've got these nonpolar molecules on top of the polar water molecules, or oil on top of vinegar, or giant oil spills, which I know that picture is just pretty much black, but oil spills on the ocean. That oil floats up to the surface, and then when seagulls or something land on it, they get coated in that oil and sometimes can't take off again. And because you can't wash off the oil without soap, they can't get the oil off. Or whales or dolphins or other things come to the surface to try and breathe, and they go up through this layer of oil. Oh, good. We do get a recap of this. So the book's method for determining whether or not something is polar is that you look at the molecule's polar bonds, and then you determine whether the polar bonds add together to form a net dipole moment, which is a lot more difficult than determining if there are no lone pairs on the central atom, and looking to see if the atoms bonded to the central atom are identical or have the same electronegativity. So this is a recap of the same rule that we used at the end of chapter 10. And yeah, just to reiterate, both of these things have to be true for it to be nonpolar. Okay, so with that in mind, and for most of these, you don't need to do like a full Lewis dot structure, but the skeletal structure can be enough. If you end up with 4 bonds to anything in this class, then you don't need to go farther than that. But if you don't end up with 4 bonds, then you might need to do a full Lewis dot structure to figure out if the central atom has any lone pairs. Okay, so for this first example, A, that's carbon tetraiodide, not chlorine. So we say carbon, and then we'll iodines around it, right? So that would be the skeletal structure. Is that polar or nonpolar? Does it have, why do you say polar? Or are you just guessing?
Is it nonpolar because it's on like this side of the periodic table?
So I'm trying to determine, like, So the bonds between carbon and iodide, the individual bonds might be polar, but we want to know if the overall molecule is polar.
I thought it was polar because, just kidding, that would only make sense. It would have 6 valence electrons in each cell. What I was going to say, it has 7. So, like you said,
Yeah.
where I was going to go, it would make the octet if it had 6 on each
Uh-huh.
iodine.
Oh, this one.
I
So,
thought it had 6.
oh, so you're thinking lone pairs on the iodines?
Well, would it be, so if it's polar, then that means there's lone pairs? I missed.
Yeah, it's okay. We just got to this, but so lone pairs, specifically on the central atom,
Would make it polar.
would make it polar.
Okay.
And then, yeah, bonded atoms to the central atom are identical or have the same electronegativity. So if there are no lone pairs on the central atom and the atoms bonded to the central atom are identical, I wanted to highlight this. Then these two things, if these things are both true, then it's nonpolar. All right, so does carbon have any lone pairs on it? It does not. It has 4 bonds, so it's not going to need any extra electrons. It's not going to have any lone pairs. And then are all the atoms bonded to the central atom the same? It's not a trick question. All right, they're all iodine. So this one is nonpolar. So if I draw a B, we're going to have hydrogen, 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 and a chlorine. So what's the first thing to check for? Are there any lone pairs on the central atom? No. Are all of the atoms bonded to carbon the same? No. And so this is going to be polar. HCl. Is it polar or nonpolar? And can you tell me why?
Is it nonpolar because the bonds or the atoms aren't the same? So like there's no like central atom.
There is no central atom, true. All right, because we only have 2. So instead use the polarity of the bond itself. So generally, hydrogen is going to be more positively charged. So if it's forming a bond with something that's a nonmetal, another nonmetal, that's going to be a polar bond.
Because they're on opposite sides of the,
Periodic table.
like the north and the south pole.
Yes. So is polar or nonpolar?
Polar.
Yeah. Alrighty. So, do a quick recap. We have dispersion forces are the weakest. Then dipole-dipole forces are stronger than that. And now stronger than that is hydrogen bonding. So hydrogen bonding is a special type of bond, only occurs in compounds where hydrogen atoms are bonded directly to fluorine, oxygen, or nitrogen. And it creates an extra strong intermolecular force. kind of like a super dipole-dipole force. And this happens because there's a large electronegativity difference between the hydrogen and the fluorine, oxygen, and nitrogen. And that allows most of the electrons to be stolen away from the hydrogen. And since the atoms are so small, it can also get really close to another hydrogen, nitrogen, or oxygen and form a sort of pseudo bond between that other hydrogen, nitrogen, or oxygen. Sorry, nitrogen, oxygen, or fluorine. So hydrogen bonds occur between molecules. It's not a covalent bond, but it has about 2 to 5% the strength of a typical covalent bond. So covalent bonds are what hold all nonpolar molecules, all molecular compounds together. Very, very strong bonds. Right? We have to use chemical reactions to break those bonds. So 2 to 5% of that strength is very strong. So for hydrofluoric acid, HF, the hydrogen on each molecule will be strongly attracted to the fluorine on its neighbor, because almost all of the electrons in the situation are going to be around the fluorine. Then it's going to be even more positive and more negative, so a larger dipole. And then the attraction of this hydrogen to the fluorine is what causes what is called the hydrogen bond. So the thing to remember is specifically if you have hydrogen bonded directly to oxygen, nitrogen, or fluorine, that's when you get hydrogen bonds. So methanol can also hydrogen bond because we have, this is oxygen. Oxygen directly bound, or hydrogen directly bound to the oxygen, creates a hydrogen bond between two separate methanol atoms, or methanol molecules. So the biggest place we can observe this effect is if we compare it again to something that doesn't have hydrogen bonding, just dispersion forces. And again, this is where it could ask this kind of question, based on these melting or boiling points, which one of these has the strongest intermolecular forces? So methanol, molar mass is 32, very similar to the molar mass of ethane. Right, so if we were thinking just dispersion forces, because remember, everything has dispersion forces, even if it has hydrogen bonding, even if it has dipole-dipole forces. So thinking just about dispersion forces, they should be about the same because they're about the same mass. But if you look at the boiling point of methanol is 64 degrees, positive 64 degrees Celsius. The boiling point of ethane is negative 88 degrees Celsius. Right, so it's 120 degree difference. Do that math right? Yeah. You did that math right. Or 100. Anyways, huge difference in 140 degree difference between those boiling points. And even the melting points, even though this melts at negative 97, which is still very cold, ethane with the same molar mass melts at negative 172 degrees Celsius. So melting point and boiling point are related to the intermolecular forces because it's telling you how much energy it takes to go to break the bonds in a solid, intermolecular forces, to make it into a liquid, and then to go onto a gas. Now, water is extra special because it forms 2 hydrogen bonds per every water molecule. right? Because when we have a hydrogen bound directly to an oxygen, you get this hydrogen bonding effect. And so one oxygen can form hydrogen bonds with two other hydrogens from other water molecules. And that's why the boiling point of water, even though it's a tiny molecule, molar mass is 18.02, its boiling point is 100 degrees C, and its melting point is 0 degrees C, which, if we go back up here, this is getting close to twice the molar mass, but its boiling point is only 64 degrees C, and its melting point is negative 97. So double hydrogen bonding makes for very, very strong, very sticky molecules. It's also the thing that holds together your DNA. So the base pairs of DNA hold the two strands together through hydrogen bonds. Nitrogen, hydrogen, and oxygen, hydrogen groups on those base pairs link up with each other, fitting almost like keys to form hydrogen bonds. So if we look at these two molecules, which of these is going to have a higher boiling point? Why do you say hydrochloride? Hydrochloric acid. So it would have stronger dispersion forces, but we also have other forces going on here. Yeah, it would be, so this would have the higher boiling point because it has hydrogen bonding. So if you have hydrogen, keep doing this. Oxygen, nitrogen, or fluorine bound directly to a hydrogen, that gives you hydrogen bonding. So that means it's got stronger intermolecular forces. So, yeah, in terms of, okay, so for a problem like this, if you got to look for either hydrogen bonding, which is stronger than dipole forces, which is stronger than dispersion forces. So if you're looking at two different molecules, if one of them has, well, let's say, okay, so if they both have dispersion forces, you look at molar masses, compare those. If one of them has the dipole-dipole force and the other one only has dispersion, dipole-dipole wins. If they both have dipole-dipole forces, then maybe use the dispersion forces on top of that to see which one's stronger. Right? Then you can use molar mass because that's going to be the difference maker. But if you get two things, one of them has hydrogen bonding, the other one only has dipole-dipole forces, doesn't matter how big this other one is, hydrogen bonding wins. So they're kind of like weight classes. Dispersion forces is featherweight. Hydrogen bonding is like heavyweight. And we have one more. So if you put, it doesn't matter if you put, a heavyweight boxer against a featherweight boxer, the heavyweight boxer is going to win. If you have two featherweights, then it's more of a competition and you got to look to other things to compare them. Moving on though, there's the super heavyweight of ion dipole force. So the ion dipole forces occur in mixtures of ionic compounds and polar compounds. So they're especially important in aqueous solutions of ionic compounds. Actually, wait. Oh, okay, I guess that's where we're stopping with that. So the ion dipole force, occurs in mixtures of ionic and polar compounds. So when sodium chloride is dissolved in water, the negative chloride ions interact with the positive poles of the water, and the positive sodium ions interact with the negative side of the water molecules. And so when you put solid sodium chloride, table salt, into water, the water molecules immediately start attacking it, and they start ripping off ions and surrounding them. And so that's the ion dipole force. So that one is the strongest. So as a summary of the forces, again, dispersion forces are the weakest. They lose to every other type of intermolecular force. Dipole-dipole forces beat dispersion forces, but lose to hydrogen bonds. Hydrogen bonds beat dipole-dipole, but they lose to ion dipole. So most likely question that I will ask is I will give you a series of compounds, and I'll say rank these based on their intermolecular forces. And I might give you boiling points. I might give you melting points. Just remember that the melting point or the boiling point of a compound depends on the intermolecular forces, how sticky they are. All right, so types of solids. Again, we've addressed most of these in one way or another, but now taking a deeper look at them. So we can have solids that are crystalline, which means that they have a well-ordered array of atoms or molecules, or they can be amorphous, meaning that they're just jumbled and mashed together. So the difference between me packing a suitcase and my wife packing a suitcase. I just throw everything inside, and then she organizes her clothes. So our crystalline solids can be divided into three categories based on the individual units that compose the solid. So molecular, ionic, or atomic crystalline solids. Nice little flow chart. This middle one is ionic solids. And for each of these, the name tells you what the individual components of that solid are going to be. For a molecular solid, it's made of molecules. For an ionic solid, it's made of ions, or formula units, cations of ions. And then for atomic solids, they're made of atoms. So molecular solids, again, are composed of molecules. Right, composite units are, oops, wrong one. Composite units are molecules. So ice, CO2, sugar, dry ice, right, solid CO2. They're held together by intermolecular forces. So those could be dispersion forces, dipole-dipole forces, and hydrogen or hydrogen forces, hydrogen bonding. Ice is held together by hydrogen bonds, while dry ice is only held together by dispersion forces. And compared to the other solids that we're going to talk about, they tend to have moderately low to moderately low melting points. So just those intermolecular forces holding them together. Ionic solids are composed of ions. And I've mentioned this a few times, but for ionic solids or ionic compounds, we'll often talk about them as just NaCl. That's actually a formula unit. The entire crystal of sodium chloride is going to be a repeating pattern of NaCl, NaCl in a grid. So there's always sodiums next to chlorines. And these are held by electrostatic forces, electrostatic attractions, which are also called ionic bonds. Those are very, very, very strong bonds. So generally, ionic solids have high melting points due to their high bond strength. For example, sodium chloride will melt at 801 degrees Celsius. atomic solids are going to vary wildly in terms of their melting points, depending on what it is. So, right, diamond's going to have a high melting point. Iron is going to have a high melting point, but noble gases like xenon are gases. So they have very, very, very low melting points. And it depends on what kind of force is holding those together. So breaking these into individual categories, we have, can you read that? Yeah, you can kind of read that. I'll do this though. This is covalent. So atomic solids that are held together by covalent bonds have very high melting points because they're held together by very strong bonds. So silicon is one that we use a lot. All of your computer chips, all of the processors in your phones made from silicon, crystal silicon. They actually grow these giant silicon crystals, cut them into wafers. Diamond is another example of a covalent atomic solid. Non-bonding atomic solids are held together just by dispersion forces. So that would be like xenon, really the noble gases, very, very low melting points. Then metallic solids are held together by weird metallic bonds, which we don't really talk much about. And those will have variable melting points from mercury, which is a liquid at room temperature, up to, I think it's osmium or iridium that has the highest melting point, something like 6,500 degrees C. So diamond, again, being another example of an atomic solid held together by covalent bonds. Every diamond is a single molecule of carbon, which is pretty wild to think about. So every carbon in that is being held in a tetrahedral shape, and then that just repeats throughout the entire thing. So it's one molecule. Very, very strong covalent bonds make for high melting points. So diamond is estimated to melt at 3,800 degrees C. Probably estimated because it'll burn before then, because it is made of carbon. Yeah, so it's making this, it's a three-dimensional hexagonal pattern. It's kind of hard to see if you don't know what you're looking for, but it's, you can highlight it, like this one, there's a hexagon. That's not very well defined. So there's a hexagon in there. All right, so long-range repeating pattern. Non-bonding atomic solids are held together just by dispersion forces. So solid xenon will melt at negative 112 degrees C. You have very low melting points. And then the reason that they're only held together by dispersion forces, especially for noble gases, is because they already have octets. So they don't want to form any bonds. They don't share any electrons. Just those instantaneous dipoles hold them together. Very weak. Metallic atomic solids will be held together by metallic bonds, which is essentially a sea, well, it's a positively charged ions and a sea of electrons. So it's all these positively charged metal ions surrounded by electrons, which is partly why they conduct electricity, because that sea of electrons can be moved one way or another. The metallic atomic solids have variable melting points because metallic bond strength varies. Right, so mercury, negative 39 degrees C, but iron melts at 1,809. And it's not even particularly a high melting point. So, simple model of metal ions all together, and then sea of electrons that can move in between. So for the most part, voice crack there. For the most part, you can use the same sort of nomenclature rules. You know how to name things, right? We named molecular compounds and we named ionic compounds. And if it's not one of those, then it's probably a atomic solid or non-bonding atomic solid. So NH3 would be what kind of solid? What rules would you use to name it? Molecular. All right, it's all nonmetals. For B, is it molecular, ionic, or atomic? Be an ionic compound or an ionic solid. It's a metal and a nonmetal. Right? Calcium oxide. And for C, molecular, ionic, atomic. It's only krypton, right? So it's atomic. All right, now we're just gonna hype up water for a bit. Water is a remarkable molecule because of this hydrogen bonding. There's really not another compound that hydrogen bonds as well. So water can form, like I said before, two hydrogen bonds from each of its hydrogens. So if you look at other things that look like hydrogen or in the same series, or look like water, that are in the same series. So if we start with oxygen, then go down to sulfur, selenium, tellurium. These boiling points are much, much lower than water's. All right, so they don't have the same strength of intermolecular forces. Water's really extreme polarity also allows it to dissolve many other polar and ionic compounds. It's the main solvent in living organisms, so it's the reason that our bodies can transport all the different minerals through our bodies, right? And life is impossible without water. And basically, if there's water somewhere, there's life. Sometimes even if that's just mold, still life. So that's why astronomers get really excited when they find water on other planets. If you can find liquid water, then maybe there's life there. Or maybe there was life there. Another remarkable property of water is actually that its density decreases as it freezes. Most things don't do that. Most things, when they freeze, they become more compact and get more dense, and so they'll sink. But water, when it freezes, actually expands, and it makes it so that ice cubes and icebergs float, which is especially important for lakes, right, aquatic life, because when the lake freezes, it just freezes on the top, and that actually creates an insulating layer that keeps the water below that warmer. If it froze from the bottom up, then it would slowly kill all of the life at the bottom, and then everything on top would run out of water, and it would just continue to freeze. Also, the freezing, though, is one of the reasons that most organisms, or the expansion is why most organisms do not survive freezing, because as the cell freezes, as the water freezes, it expands and ruptures the cell walls. This is also why food with high water content doesn't handle freezing very well. Fruits, vegetables, that kind of thing, they'll be sort of exploded by the freezing process. This is why you can't freeze yourselves and come back to life in the future. Too much cell damage. You can do it with hamsters, though. You just warm them up with the microwave. All right. That is that chapter.